Hello, guys. Welcome on Tesla Adventures. This is a very important problem in magnetostatics, and in this problem, you can see that there is a particle of mass m and charge q, which is projected in a region having a uniform magnetic field v naught. This particle is projected with the initial velocity of v naught, and the direction of velocity is perpendicular to the magnetic field. And apart from the magnetic force, there is a frictional force acting on the particle, which is given by F is equal to kV. So you can see that this force is resisting force, and this force is proportional to the instantaneous speed of the particle, and k is the positive constant. So we have to find out the radius of curvature of the particle, a path of the particle, and at the time when it has traveled a distance of mv naught by 2k, as well as we have to plot the variation of radius of curvature of the particle with time. So let us first of all analyze the motion of the particle. So let us see that obviously if this particle is projected in the magnetic field perpendicularly, so let us draw this magnetic field. So its projection is perpendicular to the magnetic field, and you can see that it would be moving in a circle initially. But as you can see that this resisting force, which is in circular motion, you can regard this force as a tangential force. So in this motion, you all know that normally without the existence of any resisting force, the path of the particle in perpendicular magnetic field is circular, and the motion is uniform circular motion, and the kinetic energy of the particle remains constant throughout because the work done by the magnetic field on the particle is zero. This is due to the fact that the magnetic field acts as a centripetal force required to rotate that particle in the circle, and therefore centripetal force is always perpendicular to the velocity of the particle, and hence we can say that the particle will always move in circle with a constant speed, and that is its motion would be uniform circular motion. But if there is a resisting force present in the motion of the particle, which is constantly acting in the opposite direction of the velocity of the particle, and it is doing a negative work done, then we can say that eventually its kinetic energy will decrease and its speed will decrease, due to which its momentum will decrease, and we know that the radius of the path of the circular motion is mv by qb. So if the momentum will decrease, then we can say that the radius will eventually decrease, and hence we can say that the path of this particle will be spiral, like that, because eventually its speed will decrease and its radius of path will decrease, obviously, and we have to find out the radius of curvature. So let us see that what will be the value of the radius of its path at any time t. For that we know that the tangential force F tangential is kV, and in fact if I use a negative sign, then this negative sign would represent a fact that this tangential force is acting in just reverse direction of the velocity. So F tangential is minus kV, and if at any instant of time, let us see that the radius, or we can say that the magnetic force acting on the particle will be QVB, and V will be in the plane which is perpendicular to the magnetic field, and therefore the angle between V and B will always be 90 degree. Okay, now let us see that F tangential is equal to MA tangential, and MA tangential will be equal to KV. Now we have already assumed that this acceleration will be decreasing, in fact this speed will be decreasing. So A tangential will be equal to kV by m, and we can write down A tangential as first of all we have to find out the radius of curvature of the path after it has traveled a distance of x naught. So let us first of all write down the A tangential as minus v dv by ds, where ds is the small distance traveled in its circular path, and this is kv by m. So you can see that dv is equal to k by m of ds, and integrating this term and 0 to s, and this is 0 to, in fact initial velocity was v naught, I guess, yes, this is no, this is v naught, yeah, and instantaneously its velocity or speed is v. So we can say that v naught minus v will be equal to k by m into s, and v will be equal to v naught minus ks by m. This will be the speed of the particle at any instant of time, but it is as a function of distance traveled. Now you can see that if we have to find out the radius of curvature, then first of all let us find out the v. So value of v at this x naught is mv naught by 2k. So let us substitute the value of x naught as mv naught by 2k. So v will be equal to v naught minus k by m into m v naught by 2k, and cancelling this k with k, m with m, so v will be equal to v naught by 2. So at this instant of time the speed v will be equal to v naught by 2, as well as we know that the radius of curvature is always v square upon a perpendicular. Now we know that this a perpendicular is the acceleration component which is perpendicular to the net velocity, and in this non-uniform circular motion the net velocity is obviously tangential, and the acceleration which is perpendicular to this net velocity is obviously centripetal, and centripetal acceleration a perpendicular is a centripetal, and it is v square by r, or we can write down that centripetal acceleration is magnetic force upon m, because the centripetal force is magnetic force. So a centripetal will be equal to F magnetic is q v b by m, and obviously at this point of time v we know is v naught by 2. We will substitute this value at the end. So the value of radius of curvature will be v square upon a perpendicular will be q v b by m. So cancelling this v with v, so this is mv by qb, and v is v naught by 2, so radius of curvature is mv naught by 2 qb. We could have also obtained this result directly by using the formula of radius mv by qb, and we can substitute that value directly in that formula. So if you are wondering that why we didn't use that formula, so we can use that method also. I was just illustrating the value of the formula of radius of curvature here. Now we have to find out the radius of curvature as a function of time also. For that we will write down the acceleration as dv by dt. So this is minus dv by dt. We are writing down the tangential acceleration as minus dv by dt in this equation. So a tangential is kv by m, and this is minus dv by dt, and that is kv by m, and dv upon v will be equal to minus k by m into dt. Integrating both the sides, you can see that the limit of velocity will be from v naught to v, and this would be ln v by v naught, and this would be minus k by m into t. Time limit would be from 0 to t. So V by V naught will be equal to e to the power minus kt by m, and V will be equal to V naught e to the power minus kt by m. So you can say that this speed as a function of time is exponential, and the radius of curvature will be mv by qb. So r would be mv naught by qb into e to the power minus kt by m. So you can say in fact that the speed and the radius of curvature would be the exponential curve, and let us first of all plot the speed. It would be like that, and the radius, this would be the v naught, and radius of the curvature would also be the exponential curve, and it would be like that. So this will be the variation of radius of curvature, and the overall path of this particle will be spiral. And we can also find out the total distance traveled by the particle in this path by using this integration. What we can do that we can apply the limits of speed from v naught to 0, because eventually finally this particle would come to rest, and here we can apply the limit from 0 to s total. So in that case, we would be, if we substitute the value of v naught 0, v0 in this formula, then s total will be m v naught by k. So this would be the total distance traveled by the particle in its complete path. And we can also find out the total distance traveled by the formula that work done by the resisting force will be equal to the change in kinetic energy. And obviously the change in kinetic energy is obviously the initial kinetic energy, which is half mv naught square, minus final kinetic energy, which is 0. So this was a good illustration about the spiral path of the particle in magnetic field. In the next video, we'll be bringing some more concept illustration problems. Thank you.